Standard subsets of real numbers, \mathbar$. Welcome, everyone. Before we dive into today's topic, let's take a moment to reflect on what we have already covered. In our previous lessons, we explored the general definition of a subset, learning how one collection of objects can be entirely contained within another. Now, in this new subsection, we are going to take those foundational concepts and apply them specifically to a very important set, the set of real numbers, which we denote with the symbol R. As you can imagine, the set of real numbers is incredibly vast. It is a massive collection that encompasses almost every number you have ever encountered in your mathematical journey, from simple whole numbers to complex decimals. Because this set is so large and diverse, it can feel a bit overwhelming to study all at once. Therefore, to make our study more organized and manageable, we are going to categorize these real numbers into several standard, well-defined subsets that we will explore one by one. 1. Natural numbers, \mathbb$. Now that we've established that we are looking at the subsets of the real number system, let's start with the most fundamental building block, the natural numbers. You might already know these simply as counting numbers. By definition, the set of natural numbers, which we denote with the symbol n, consists of all positive integers, beginning with the number 1. If we were to write this out in mathematical notation, we would say n equals the set containing 1, 2, 3, and so on, continuing infinitely. To make this concrete, think about a real-world scenario, like counting the number of students in a classroom. When you begin your count, you start with the first student, which is 1. You move to the next student, making it 2. You continue this process one by one, and as you'll notice, you aren't using any fractions or negative numbers in this process. Because your final total will always be a positive whole number, we can conclude that this total count is always an element of the set of natural numbers. This simple set of numbers will actually serve as the foundation for the next set we discuss, which expands these numbers to include 0 and negatives. 2 integers, \mathbb$. Now that we have a solid understanding of natural numbers, those basic counting numbers we use to tally objects, let's expand our horizons. On this slide, we are looking at the set of integers, which we denote with the symbol z. Think of the set of integers as an expansion of the natural numbers we just discussed. While natural numbers only take us from 1 upwards, the set of integers expands that collection to include 0 and even negative values. To be precise, the definition of the set z includes all whole numbers. This means all positive integers, all negative integers, and the number 0 itself. If we look at the mathematical notation, we write it as z equals ellipsis, -2, -1, 0, 1, 2, and so on, ending with an ellipsis to show it continues infinitely in both directions. To make this concept more concrete, let's look at a real-world example, measuring temperature in degrees Celsius. First, imagine a warm day where the temperature is above freezing. We can represent this with a positive integer, such as 25 degrees Celsius. Next, consider the freezing point of water, which is exactly 0 degrees Celsius. Finally, think about a very cold winter day where the temperature drops below freezing. We would represent this using a negative integer, like -10 degrees Celsius. In conclusion, because all these different temperature values, positive, negative, and 0, are part of this collection, we can say they all belong to the set z. This sets the stage for our next topic, where we will see how these integers can be further divided into fractions, known as rational numbers. 3. Rational numbers, \mathbb$. Essentially, rational numbers are those that can be expressed as a ratio, or a fraction, of 2 integers. To be more precise, the formal definition is that a number is rational if it can be written in the form p over q, where both p and q are integers, and most importantly, q is not equal to 0. We use this specific notation to represent the set. Q equals the set of all x, such that x equals p over q, where p and q are elements of the set of integers, and q is not equal to 0. To make this concept more concrete, let's look at a real-world example involving a pizza. Imagine you have one whole pizza and you want to divide it equally among 4 friends. Following the process step by step, first, you start with one whole pizza. Second, you divide that pizza into 4 equal parts. Third, each person receives 1/4 of the pizza. If we look at this result, 1/4, we can see that the numerator, 1, and the denominator, 4, are both integers, and our denominator is certainly not 0. Therefore, we can conclude that the value 1/4 is an element of the set of rational numbers. Now that we have covered natural numbers and integers, let's move on to a much broader category, rational numbers, which we denote with the symbol Q. This leads us perfectly into our next topic, where we will look at numbers that simply cannot be written in this fractional form. 4. Irrational numbers, \mathbb. Now that we have explored the rational numbers, which we can easily write as fractions, let's look at their counterpart. The irrational numbers, which we denote with the symbol T. Irrational numbers are real numbers that simply cannot be expressed as a simple fraction. To be more precise with our definition, a real number is considered irrational if it is impossible to write it as a ratio of 2 integers. If you were to look at their decimal expansions, you would notice 2 very important characteristics. They are non-terminating, meaning they never end, and they are non-recurring, meaning they never settle into a repeating pattern. In mathematical notation, we express this as the set T is equal to the set of all x, such that x is an element of the set of real numbers, and x is not an element of the set of rational numbers. Essentially, if it's real but not rational, it must be irrational. To make this concrete, let's look at the most famous example, the number pi. First, remember that pi represents the ratio of a circle's circumference to its diameter. Second, if we look at its decimal value, it is approximately 3.14159, and it continues forever without ever repeating a pattern. Finally, because this value cannot be written exactly as p over q, where p and q are integers, we conclude that pi is an element of the set T. This brings us to a very important point that we will see in the next slide. How all these different sets, the natural numbers, integers, rational and irrational numbers, actually fit together into one big hierarchy. The hierarchy of number systems. Now that we have defined each of these number sets individually, natural, integers, rational, and irrational, let's bring it all together to see how they relate to one another. If you look at the first bullet point, you'll see that the relationship between these sets is one of inclusion. In mathematics, this simply means that some of these sets are entirely contained within others, much like how a small box might fit inside a larger one. Let's trace this from the inside out. First, we have n is a subset of z. This means every natural number, such as the number 5, is also an integer. Next, we see that z is a subset of q. This is because every integer, like -3, can be written as a fraction, specifically -3 over 1. Because it can be written as a ratio, every integer is also a rational number. Continuing this pattern, q is a subset of r. Every rational number we've discussed is, by its very definition, a real number. When we combine these observations, we get a beautiful, continuous chain of subsets. N is a subset of z, which is a subset of q, which is a subset of r. It's like a nesting doll of numbers. However, don't forget about the irrational numbers we just studied. The set T is also a subset of the real numbers, r. Now, here is a very important note to keep in mind before we move on to our summary. The set of rational numbers, q, and the set of irrational numbers, t, are disjoint sets. This is a fancy way of saying they have no overlap at all. No number can ever be both rational and irrational at the same time. But when you combine them, they perfectly complete the entire collection of real numbers, r. Key takeaways. All right, let's take a moment to pause and recap everything we have covered in this lesson. This slide serves as a summary of the key points to ensure you have a clear grasp of the number system hierarchy before we move on to some common pitfalls. First, we have the natural numbers, denoted by the symbol, and these are your basic counting numbers, starting from 1 and going up infinitely, like 1, 2, 3, and so on. Next, we have the integers, represented by the symbol z. This set is broader because it includes all those natural numbers, but it also brings in 0 and all the negative whole numbers, such as -1, 0, and 1. Then, we move to the rational numbers, which we denote with the symbol q as we discussed with the pizza example. These are any numbers that can be expressed as a fraction or p over q, where both p and q are integers and q is not 0. On the other hand, we have the irrational numbers, denoted by the symbol t. These are the real numbers that simply cannot be written as a simple fraction. Their decimals go on forever without any repeating pattern. To tie it all together, look at this subset chain. N is a subset of z, which is a subset of q, which is a subset of r. This notation shows that each group we've studied is contained within the next, eventually forming the complete set of real numbers, r. Keep this hierarchy in mind, because in our next slide, we will look at some common mistakes students make when trying to distinguish between these specific groups. Common mistakes. First, let's address a very common confusion between rational numbers, which we denote as q, and irrational numbers, which we denote as t. A frequent mistake is assuming that any number containing a decimal point must be irrational. This is simply not true. Take, for example, the number 0.5. While it is written as a decimal, it can be perfectly expressed as the fraction 1 over 2. Because it can be written as a ratio of two integers, it is actually a rational number, or part of the set q. Remember, a number is only irrational if its decimal expansion goes on forever without ever settling into a repeating pattern. Next, let's clarify the status of the number 0. This is a subtle point that often trips people up. Based on the standard definitions we've used today, 0 is definitely an integer, belonging to the set z, and it is also a rational number, belonging to the set q. However, it is important to remember that 0 is not considered a natural number, or part of the set, and our counting numbers start strictly at 1. Finally, when you are writing out the formal definition for rational numbers, specifically when expressing them as p over q, you must always include the condition that q is not equal to 0. In mathematics, division by 0 is undefined, so specifying that the denominator cannot be 0 is crucial for a mathematically sound definition. Now, before we wrap up today's lesson, I want to touch upon some common pitfalls that students often encounter when working with these number sets. Paying attention to these nuances will help you avoid errors in more complex problems later on. Keep these distinctions in mind, and you'll have a much stronger grasp of the real number system.